All right, everybody. I hope you had a nice Christmas vacation. Welcome back. Till you guys see you actually did write it out. Something about the Northwest Passage. Yeah, that homework was a joke. It was sort of a impossible task you're not supposed to be able to do.
I slammed the revolving door.
You did? Nice.
Found my calendar example.
Huh?
Found the calendar example for it.
For P equals P. Well, submit it to the Cray Institute, you can win $1 million.
Yeah, I thought that was really hard to be forever.
So, that's always a fun one to put as those things. But anyway, in all honesty though, we did have for today an actual assignment due. And some of you asked me questions about it last night when I was on duty, which is fine. I want to go over that real briefly to make sure you guys remember what it's like. Okay. Essentially, it was what we'd done right before going on break, and that was looking at integrals by substitution. Okay. Yeah. Okay. So this is page 306. Okay. As a quick refresh of how the substitution method works. Okay. Basically, you do integration by substitution. This works, this is essentially the chain rule in reverse, okay? Okay, so it essentially is working on derivatives. It's working on the derivative to get back to the original function, okay? So if you remember the chain rule, what that one looks like would be that if we took the derivative of a composite function, f of g of x, it comes out to be f prime of g of x times g prime of x, okay? Well, the substitution method reverses this. Okay? Basically how it works is we're going to start off with an integral, okay, typically written as, go away, I said go away, shoot, f of g of x dx, okay, and what we do is we define any random variable. The one that's traditionally used is u. We would come through and we would say u will set that equal to g of x. Okay. Then the derivative of u. Okay. Oh, I'm leaving off a step right here. Sorry. Hold on, guys. Oop. I'll put this in correctly. There we go. Then the derivative of u would be g prime of x dx. And so that lets me rewrite my integral here. Okay, replacing g of x and g prime of x with u and du respectively. And the benefit there is, what happens, okay, is I get a single, I now have something I can take the antiderivative of directly, okay? Because that antiderivative is just going to be what? Big F of u plus c, right? Okay. So, how this is working here is, again, if I could see that my problem is written as such, that is, if I could tell if I could identify something as being a function, like g of x, and then see that its derivative is also in the problem, I can do this, what's called u substitution to it, to be able to solve it out forward, okay? That's what we looked at before break, for those of you guys who might remember, okay? But this is essentially what we're doing. So, looking at the homework from last night, all the problems were ones in which we were doing that sort of thing. So if we look at number 11, the very first problem, okay, we had 1 plus 6x to the 4th power times 6 dx, okay? And so the idea here is I want to identify something to be a function in here to be u, and then see if the derivative of u exists also in the function, okay? So what would I choose to be u in this case?
Go with the higher exponent.
1 plus 6x, right? Because I could say, well, if u is 1 plus 6x, du then becomes just 6 dx. Do I have all those pieces in my problem?
No.
Yeah, absolutely. Okay, there's u, okay, and there's du, okay? So I can then rewrite this whole thing as just the integral of u to the 4th du, and the integral of u to the 4th is easy, right? See if the derivative of u to the 4th. U to the 5th over 5. What else am I leaving off there? Plus c, because this is indefinite. Okay? And that's your answer. Okay?
Well, what do you do with the 6dx? Nothing?
Yeah, it goes away. Okay? Because what's happening here, Teddy, is this thing is a chain rule in reverse. Okay? So the 6dx, okay, that became the du, gets basically assumed back into the original problem. It's the same reason why every time we have a dx on a normal integration problem, we don't do anything with it. Same thing here. The du became was 6dx. Well, in our final product there, okay, we just have a du, and so it just goes away. Okay. If you're unsure of that, if you're like, well, that seems kind of off, I'm not used to that sort of thing, go ahead and do as the books suggest and check this using the derivative. That is, take our final product there, u to the 5th over 5 plus c, and take the derivative of it, okay? And see if we get back what we started with. So we're going to do the derivative with respect to x of u to the 5th over 5 plus c. Well, u to the 5th, well, u is 1 plus 6x, right? So we can go ahead and make that, put that back in. Okay, just like so. Now, the derivative of this guy here, okay, how would I approach that? I would use what rule?
The
Chain rule, right? Okay, that 5 at the bottom is a constant, so we're not going to bother. We don't really want to use the quotient rule here. I can rewrite that as 1/5 times all this, if I really wanted to. But this top part here, I'd have to use the chain rule. The chain rule says, take the derivative of the outside first. So what's the derivative of something to the 5th? 5 something to the 4th, right? So this would become 5. The 1 plus 6x doesn't change. Okay? But then we multiply by the derivative of the inside, right? What's the derivative of 1 plus 6x? 6. And finally, plus, what's the derivative of c?
1.
0. Okay, again, it's a constant. Derivatives of constants are zeros. So we have plus 0 there. Okay? And so, right there, what's going to happen to those 5s? They cancel, and the 0 is just 0, so we don't care about it. 1 plus 6x to the 4th times 6. Isn't that the same thing as what we started with? Yep. Okay, so we can see here the chain rule indeed does work. Okay, or sorry, not chain rule, but the substitution method allows us to handle it. Okay. Again, as a reminder to you all, what you're doing with substitution is you're reversing the chain rule, so you're always looking for a function and its derivative in a problem. Okay. And working things out that way. Kind of as a general rule of thumb, okay, or as a general idea of when you approach these things, a lot of times people have trouble identifying what U should be in the problem. And I've always found that kind of strange. U should always be the, is almost, and this is going to be the case for 99% of these things, U is going to be the thing with, the part with the x, or whatever part has the x to the highest exponent, okay? Or, and most of the time it's both. U is going to be the thing that's inside parentheses raised to a power, okay? So if you look right here, I knew 1 plus 6x had to be what U was, because 1, that's the only thing with an x in there, and 2, that's inside parentheses, right? Being raised to the 4th power. So that's a dead giveaway that that should be U, okay? And then from there, everything else follows. The other big thing with these things, and this is where, again, people sometimes have trouble, is, and we'll see this in one of the next problems we do here, is that oftentimes, too, people have trouble figuring out exactly what du is, okay? It's kind of weird, but you identify what u is, and then take the derivative of u to see what du should be, okay? So it's not like I say, well, this is u, that means everything else must be du. No, I have to actually take the derivative of this first to figure out what du is, and then see if I have it in my problem, okay? If I don't have it, I gotta see if I can either put it in, and if I can't put it in, then I can't use substitution here, okay? Which happens, okay? They look like you can use substitution, they really can't, okay? Any questions on the methods, though, I used here? All right, let's take a look at the next example, okay, from homework. Let's do 15, because 15 illustrates well what I'm after here, okay? So 15, we've got the indefinite integral of x cubed times x to the 4th plus what? Plus 3. That's a terrible looking 3. Make that a nice looking. Squared dx. Okay? Alright, so on this one right here, right off the bat, okay, first answer this question. Is this something I can do normal integration to? No, well, at least not as it's written, okay? To be perfectly honest with you, x to the 4th plus 3 is easy enough to square. You could square that out, then multiply it all by x cubed, and then have something, a regular old polynomial, which you can do integration to. However, that's going to take a long time to do, right? And we want to do things faster. So we're not going to do this with normal integration, we're going to do this with some other method, okay? Which means we're going to do it by substitution, because that's the only other method we know, okay? So we've already determined we're going to try substitution on this one. So if we're going to do this by substitution, what are we going to pick to be our u?
X to the 4th plus 3.
Okay, I'm going to say that nice and loud.
X to the 4th plus 3.
X to the 4th plus 3. Why?
It's a binary.
Okay.
That's the highest power.
Okay, it's the highest power, and, as you said, it's in parentheses. Okay, that right there should be the reason, is plenty of reason why we want to pick that to be u. Okay, x to the 4th is the highest powered x in the entire thing, and it's also inside a set of parentheses being squared. Okay, so that's the reason why we want to choose that to be u. Okay, so u then is going to be x to the 4th plus 3, because when you choose something, you have to choose all of it. Okay, and so the plus 3 goes with it. Okay, that means ignoring this now, concentrating just on this, what should du be?
X to the 3x cubed dx.
Okay,
4x cubed.
is it just x cubed dx?
It's
What's
4x
this thing?
cubed. 4x cubed.
It's 4x cubed dx. Okay, 4x cubed dx. Okay, so looking above here, do I have 4x cubed dx?
No.
No.
I've got one.
I've got x cubed, I've got dx, but I'm missing a 4, right? Okay. Now, it might seem like, oh, we're done then. We can't do this by substitution. But 4 is just a constant, right? It's a constant that is being multiplied through, right? So there's no reason why I can't add a 4 to this, as long as I add its reciprocal to the outside. Okay. If you remember, kind of as a quick review here, a constant scalar can be moved in and out of the integration, the integrand, as you need. Okay. So if I have the integral of a constant k times f of x dx, that's the same thing as the constant k times the integral of f of x dx. That was one of the properties of integration we learned before. Okay? So, I need a 4 in here, so there's no reason I can't put a 4 in there. But if I put a 4 in there, I also have to put a 1/4 in there as well. Why 1/4? Makes it 1. What's 4 times 1/4 is 1. And if I multiply something by 1, do I change its value? Nope.
Just tiny bit.
So, I'm going to come through here and I'm going to add in my 4, okay? But I'm going to also add in a 1/4, okay? And I could get away with this, again, from this property of integrals that we've seen before. And because of the fact that I can pull that 4 back out, make it 1, goes away, okay? Or I can put the 1/4 back in, make it 1, goes away. But by doing that, now I've got all my pieces. Okay.
How do you know you're supposed to put 4 in there?
I know I had to have a 4 in there because right down here with du, away, shoo, okay? My du had the extra 4 in there.
Where
Okay.
did you get that?
Where did I get that du?
No, where did you get that 4? I know where you got the DU actually third.
Okay. Where did I get the 4 there?
Yeah.
I had to, because there was a 4 in du, I had to add a 4 to my problem.
I know, where did you get the 4 in DU?
It's the derivative of x to the 4th plus 3.
Yeah, okay, sorry.
So, remember, again, this is why I say, and this is the thing that confuses a lot of people with u substitution, when figuring out what du should be, you ignore, once you've determined what u is, forget the integral, and just concentrate on what u is, okay? Take the derivative of this thing in front of you, the x to the 4th plus 3. Derivative of x to the 4th plus 3 we know is 4x cubed. That's where that 4 comes in, okay? And that's why, after I determine that that's the derivative of du, or sorry, that's the derivative of u, I have to see if I have it in my original problem, okay? So I did that step, then I went back up here, look, do I have my du? Well, I have most of it. I was missing a piece, but the piece I was missing was just a constant, so I could add it in, okay?
So if you add the constant, you have to add the reciprocal of the constant outside of it.
Yep, just like we did up there. Okay, because if I added it without the reciprocal, I'm changing the value of the function. And that I'm not supposed to be able to do. Okay? So, now that we've done that, we've got all our pieces here, we can do a u substitution. Okay? We're going to have this become u squared du, but on the outside, there's still a 1/4. Okay? That 1/4 was out, we wrote it in such a way where it's outside the integrand. So it has to sit out there still, okay? But it's just a constant, so we just, it's just a constant multiplied. It's a scalar, we just let it be, and we just concentrate on doing this integral. What's the antiderivative of u squared? It's what?
It's u cubed over 3.
U cubed over 3 plus c, and then out in front of that all is still
1/4, so it'd be a 12.
the 1/4, okay? And if you wanted to write your final answer out, yeah, you could write it as u cubed over 12, okay? Plus c. You don't have to write c to the 4th, okay? You can if you wanted to, but I wouldn't. C is just a constant, okay? It's an unknown constant that we know should be there. Multiplying it by 1/4 keeps it as an unknown constant that we know that should be there. So we just write it as c, okay? All right. Any questions there? Okay. But that's how they come out to be. Okay, let's look at another one of these. Ooh, 21. 21 is very good. Okay? Because 21 is going to be like one of these right here. Okay?
You only do 23, not 21.
23 and 21?
That'd
You want to see 23?
be- Yeah.
Okay, let's do 23 then. Okay, so 23, we've got the integral of x over 1 minus x squared cubed dx, like so. Okay? Yeah, I got that right. Okay. First question you should ask yourself is, can I do this normally? No. Okay. We don't have any tools or rules to handle something like this.
So I don't get what you mean normally.
Normally, I mean, can I just do a regular antiderivative? So, for example, if I had the integral of 3x to the fifth dx, that I can just take the antiderivative, right? Okay. The 3x to the sixth over 6 plus c. Okay. That's all I have to do. Well. That's what I mean by normally. Well, I can't do that here, can I? Okay? Nor can I rewrite this thing so I can make it something like that to do easily. Okay? So, that means I'm going to then switch over to substitution mode. Can I write this as a substitution? Okay? If I could, what would I pick to be my u, my substitution variable? 1 minus x squared. Why?
Bigger x, bigger x.
Bigger x in parentheses. Those are good enough reasons right there. Okay. U, it's going to be 1 minus x squared. Then ignoring this thing is twitching out on me today. So ignoring the rest of the integral, what's du going to be?
Number 2x. Yeah.
Negative 2x. Okay? All right, good. So, coming through up here, okay, this right there is u, okay? That right there is most of du, right? What am I missing though?
2, or negative 2.
A negative 2. So, I can put the negative 2 in there, but what do I have to put on the outside?
Negative 1.
Negative 1/2. So I'm going to add negative 2 to the top and put a negative 1/2 on the outside. Okay. Now I can do my substitution. We have a negative 1/2 still on the outside. The integral of the x dx, the negative 2x dx becomes du. On the bottom I have u to the third. Okay. Just like so. Now, what do I have to do to the u to the third in order to do this integral? Do I want to leave it down there?
Negative.
No, I'm going to bring it up with a negative exponent, right?
I see now.
And that should be an easy enough antiderivative to take, right? What's the antiderivative of that? There we go. U to the negative second over negative 2 plus c. Okay. You can leave your answer like that. Actually make that look like a negative 2 on the bottom and not some sort of weird character. There you go. That's perfectly acceptable to leave your answer that way. By the way, I've been leaving all my answers in terms of u. You could do that. Okay. There's no reason why you can't do that. There's a few instances where you will want to put back in what u was. Okay. So u was 1 minus x squared. So I might want to, in certain cases, replace u with 1 minus x squared and go from there. Okay. But for the most part, this is all you have to do. Okay. Any questions? All right, excellent. Okay, that's about as nasty as they come. Okay. All right. So, there's no other questions about substitution. That should be a good review for you all. Okay. How many of you attempted this homework? Okay. All right, good. So So most of you did. If you didn't, try to go back through it and do it, because we're getting into the process now of getting ready for that AP exam in May, okay? I know it's January. I know it's what, January what, 5th? 6th. So I'm a day behind now. But still, it's time for us to start thinking ahead, okay? I'm not gonna collect, I said last night I would collect the homework. I'm not going to. I'll let you keep it. But tomorrow, whatever's assigned, I am gonna collect at the beginning. Make sure you guys are doing it, okay? We keep also, too, give you a heads up for tomorrow, and just in general what to expect, kind of going forward. Tomorrow, we're going to have the first of what are called power quizzes, okay? What these are is, they're very short quizzes, basically designed to get you to drill constantly common things. So these are all always based on something that's just, you gotta know it, okay, sort of situation. So tomorrow, the first power quiz is going to be on the derivatives only, okay? And the questions you're going to see, basically, it's just quick one-off, what's the derivative of this, okay? So kind of the level of difficulty you should expect here would be something like, what's the derivative of x cubed? What is it?
3x squared.
3x squared, okay? Or, what's the derivative of the sine of x?
Cosine of x.
Cosine of x, okay? That sort of thing, okay? Just rapid fire drill, okay? It's the type of idea that you either, and basically, I am gonna time these as well, okay? Because the idea is to get them through quickly, okay? And it's a sort of situation you either know it or you don't. So it's like, there's no sense of sitting there like going, oh, I don't know if I'm doing this right, because if you're sitting there going, I don't know if I'm doing this right, then you're not doing it right. It's automatically just, the idea is to get you used to kind of the rapid fire that you will need as preparation for the AP, okay? Everyone got that?
Jim, so when you're on what we were doing that last problem, what's the point in adding, can you get back to the last
Yeah.
one? What's the point in adding the -2 up there on the first one if you're just not going to include it in the substitution?
Okay. Why did I put the -2 up here? Okay. I need du, okay? As part of the substitution, I need to replace a bunch of stuff with du,
Yeah.
okay? When I chose u to be 1 minus x squared. That meant du had to be minus, excuse me, sorry, had to be minus 2x,
Yeah.
okay? Well, my original problem, I had x and dx, but I didn't have the -2. So that's why I put the -2 in there. And I did include the substitution. The -2, okay, x dx is what became du.
Okay.
Okay, and then from there, taking the derivative of it is, or not taking it, once we've done that, the rest is just a regular integration problem. Okay, it comes out that way. And a regular integration, that du or that dx always just kind of goes away. Okay, and so that's what happened here. But that's why that's what happened to the -2. Okay, that's why we had to add it in. Okay. Basically, what really was more important is the fact that we put that -1/2 out in the beginning.
Yeah, that's what I was.
And the reason for that is because that counterbalances the fact that we had to put a -2 in there,
Yeah.
okay? Because -1/2 times -2 is 1, and so it cancels everything. It doesn't, doesn't affect things. But it does affect your final answer, having the -1/2 out there. Because if I were to, again, like I did earlier, like I did in the very first problem, if I were to stick 1 minus x squared back into the original problem and then do the derivative of it, okay, in order to get what I started with, I'm going to have to add that -1/2 out in front. If it wasn't there, okay, my answer they wouldn't be identical. They wouldn't line up correctly, okay? So that's why we've got it in there, okay? All right. Better now? Okay. So, okay. Any other questions on how the substitution method? Yeah.
So when you did the integral, the last step, I thought you add the exponent, and then divide by the new exponent.
I did. It's minus 3 plus 1.
Yeah.
Minus
Got
2.
it. Yeah.
That's something, again, that's a very, I can't tell you how many times I see students do that. They make it minus 4 over negative 4, because, you know, minus 4 is bigger than minus 3, right? Well, no. It's the other way around. We're negative, so everything will. Okay. All right, excellent. What we're going to look at now, kind of in the last 10 minutes of class, is we're going to start looking more so at things called differential equations. Oh. Why did that one come up? Okay. Okay. I'm not entirely sure why the one F decided it needed to be that color, but whatever. Okay. Now, differential equations, okay, it's just right now all you really need to know is it's a fancy way of saying that the function I'm giving is the derivative of something else, okay? So basically, the way to think of it is the function of the given function dash equation is the derivative of another function, okay? And I'm going to add in here is often, oops, often these are done implicitly. Okay, so if you remember implicit differentiation, we had the y involved. A lot of times these differential equations are written in implicitly. So you have x's and y's in the equation, okay? Now, we're going to start off with some easy ones, okay, that don't have the y in them, so we don't have to worry about the y all that much, okay? And the idea is we're just kind of working backwards to recreate the original equations, okay? So, an example of what a differential equation might look like, okay, is they're always written as dy by dx, or d of some variable by d of some other variable, is equal to, and then whatever our function is. So it could be like, or equation, so, or just equation. Yeah. So that's how they're always, when you see something like that, you know you're dealing with a differential equation. Okay. Oftentimes, too, you're told this is a differential equation. Kind of the reason why we look at them is they allow us to generalize certain equations, so that way we can write out what the equation should look like regardless of where it is along a graph, okay? So we don't have, basically we just don't have x or y in the graph, we just kind of let it be. And that lets us do something, create things, it lets us do other work. So it lets us, for example, in a physics equation say, okay, if these are the starting parameters, what does the answer come out to be? But if I change, my starting equations, what does the final product come out to be? So let's say, it's almost like saying, let's start with the speed being 10 miles per hour. What's my answer come out to be? Okay, if I change things and make it 25 miles per hour, what would the answer come out to be? Okay, that's sort of what the benefit of them, okay? So it kind of lets you play around with that. Kind of the biggest use that we're going to have is we're going to use them to create something called a slope field, which is just kind of what the slope of that particular equation will look like at any particular given xy coordinate. And we'll make one up here in a second, okay? They're not that difficult at all, okay? But this is kind of this is how they look like. And a lot of times with a differential equation, we want to get back to the original equation, okay? And how we'll do that is we would use the integral. We take the integral of both sides, okay, and come up with y equals the original equation, okay? So this is what we're doing here. So let's look at an actual example of one, okay? Using numbers. So our first one might be something along the lines of like dy by dx is equal to 3x squared plus 2, okay? So what's that saying is that you know, kind of the change in y with respect to the change in x can be written as its own separate equation, being 3x squared plus 2, okay? And so if I'm doing a lot of work, that's one of the things I deal with. If I wanted the original function back, okay, what I do is I do a quick rewrite here. Okay, and then take the integral of both sides. Okay, what would the integral of dy be? So I'm taking the integral with respect to y now. Okay? If there's nothing there, there's actually a what? Is it a 0 or a 1? A 1, right? And what would the integral of 1 be? X. But in this case, are we either doing x or are we doing y? Y, so it's y, right? So over here, the integral of dy always comes out to become y, okay? Which is good. That's what we want, because on the other side, we've got a regular integration question now. 3x squared plus 2. What's the antiderivative of 3x squared plus 2?
X cubed.
X cubed plus 2x.
3x cubed over 3 plus 2x plus c, right? Okay, so basically what I'm trying to get here is, okay, is it's not going to work any differently really than a regular integration question does, okay? It's just sort of one that's rewritten in a weird manner. Where these things would get difficult, or where you would have problems arise, is if there's also a y over here, okay, which can happen, right? In that case, you have to do what's called a separation of variables. You have to get your y's on one side and your x's on the other. And then you just proceed doing the integral of both sides. Just the side with y, you're doing the integral with respect to y. The side with x, you're doing it with respect to x. Okay? But that's how these things typically work. Okay? So, you know, if you saw one of these things, I asked, what's the integral? What's the original equation? Or rather, what equation has a derivative of 3x squared plus 2, this is how you would go through it, okay? Any questions about that so far? Okay. Now, a lot of times, too, you're going to be asked to solve the differential equation, okay? You could be told to solve it in the general sense, in which case you're done once you get it in terms like this, okay? Or you might be told to solve it for a specific point, okay? And that's where things get a little bit different. If I'm asking to solve it for a specific point, what does that mean I'm actually looking for? C, okay? So if I just said solve it, I'm done. But if I said solve it for the point 1, 5, okay, what that means I'd have to do is figure out what C is, and I would put in 1 for x and 5 for y, and then solve for c, and then rewrite my answer with the new c involved. Okay? Yes?
What's the point of doing putting in the integrands if we just ended up doing the antiderivative of what we were given at the top?
It's because you'll get, again, this is a very simple example of one. Okay? What you'll often get a lot of times is these things with a y involved in them somewhere, or we're going to use this for something else, okay? So this is just the first introduction you're going to see in these things, okay? We'll be doing a lot more work with them moving forward, okay? Is that,
Yeah.
okay? So yes, right now it looks like this is silly and stupid, but again, as we move forward, we'll get more things involved, okay? So this is an example of how a typical differential equation works, okay? So this would be the general solution. Okay? If I ask for a specific solution, so let's find a solution. Okay? What I would do there is replace, do the same exact thing, but replace the y and the x with their various numbers. So this would become 5 equals 3 times 1 cubed over 3 plus 2 times 1 plus c. And what am I solving there for? C, right? And then I would get whatever c is and pop that back into the original equation. Note though, any 2 points could be possible solutions to this thing, right? I could choose another set of points and get a completely different answer, wouldn't I? I have a different C, okay? And so that's sort of why you have the general solutions and the specific solutions as we run through here, okay? All right, and that brings us to, and you guys are packing up, which means I know we're out of time. And so I'll have to just adjust the assignment tonight accordingly. But that brings us to something known as the slope field, which we'll look at tomorrow in class, okay? Which is basically a graphical representation of what the equation does for various points, okay, as you move through, okay? All right, good. Everyone have a good morning, and I will see you tomorrow.